Since sine and cosine form the basis of our understanding of things like cellular network signals, television, radio signals, electrical waves, and basically anything to do with electronics, the unit circle and trigonometric ratios and functions bear some further consideration. Right? So we've got a circle here with a radius of 1, and theta, or this inside angle here, is created when we measure the distance or the measure from the x-axis moving counterclockwise in accordance with our 1, 2, 3, and 4 quadrants here. So we're moving through the quadrants counterclockwise, and we'll get an angle theta created between that radius and the x-axis. Right? And so if you remember from earlier in trigonometry and geometry, right, we've got a 1 is our radius again because the unit circle has a radius of 1. And then we're going to get an opposite and an adjacent side of that angle theta. Right? And we know that 1 squared, or 1, is equal to a squared plus o squared. We should also know that sine theta is the opposite over the hypotenuse, or the opposite over 1. Right? We know that cosine theta is the adjacent over the hypotenuse, or a over 1, or a. And then the tangent theta is equal to the opposite over the adjacent. And so this point on the edge of on the circumference of the unit circle at the end of that radius is the ordered pair cosine theta, sine theta, because sine theta is opposite over 1, cosine is adjacent over 1. And then tangent, we could form, remember a tangent line forms a right angle with the radius at that point. And so tangent is this this leg of the right triangle, which would form a hypotenuse of secant theta. Cotangent theta is the corresponding or complementary part that extends from that tangent point up to the y-axis, and then cosecant is that measure on the y-axis there. Remember that cosecant theta is 1 over sine theta, secant theta is 1 over cosine theta, and cotangent theta is 1 over tangent theta. Right, those are basic trigonometric identities or ratios. And so let's have a further look at Pythagorean identities. And they are, just as they sound, related to the Pythagorean Theorem. And so if we've got a right angle in here, we know that 1 is equal to, or 1 squared is equal to sine squared theta plus cosine squared theta. And that's our basic Pythagorean identity. And from there, we can do a little bit of algebra. We can subtract sine or cosine over to the other side. So we get sine squared theta is equal to 1 minus cosine squared theta. Then we can divide both sides by sine squared theta, and we end up getting 1. Sine squared theta divided by itself is 1. And that's equal then to 1 over sine squared theta minus cosine squared theta over sine squared theta. And we can then simplify. So 1 over sine is cosecant, so this is cosecant squared theta minus cotangent squared theta. If tangent is sine over cosine, or opposite over adjacent, sine over cosine, then the opposite of that, the reciprocal, is cosine over sine. And in order to deal with this squared, we'll just make cotangent squared. So this is another one of our trigonometric identities. We could have subtracted sine over the other side, in which case we would get 1 minus sine squared theta is equal to cosine squared theta. And so again, we can do that same type of algebra, and we get 1 over cosine squared theta minus sine squared theta over cosine squared theta is equal to 1, because cosine squared theta divided by itself is 1. And then simplify, 1 over cosine is secant, and so 1 over cosine squared is secant squared theta minus tangent squared theta. That's equal to 1. And we could do some further manipulation, so we would get 1 plus cotangent squared theta equals cosecant squared theta, or 1 plus tangent squared theta equals secant squared theta. And so we can move these quantities across the equal sign with some simple algebra. But the main idea here is that we're moving from that geometric side 1, side 2, and hypotenuse, or a squared, b squared, and c squared for our Pythagorean theorem, where we have a, b, and c, and then a squared plus b squared equals c squared. We're moving from this, applying it to the unit circle, and then coming up with these trigonometric ratios, which give us our sine and cosine that are later used in wave form in order to study very crucial elements of our electrical, electronic, and other signal processing in engineering, right? So these have very, very real-world applications, such that I wouldn't be able to make this video without somebody along through history having understood these very rudimentary facts and then applied them through materials and by manipulating electrical signals such that the camera would capture both the sight, the light, and the sound that are projected from me and my surroundings. And then through kind of the magic of electronics would then process that, put it into digital signal form, which no longer would follow that sine and cosine because digital is just ones and zeros. But through some sort of filtering and processing, we can compress that and change it into digital signal process, digital signal form, and then transfer between computers. And again, through the magic of what starts with this rudimentary or basic knowledge, we get all of these fantastic electronic and interactive multimedia, right? So while it might seem this stuff is kind of abstract and boring and drab and off into space, detached from the real world, in fact, these are the building blocks of these much more complex systems that we're all interacting with every day. And as Elmo likes to say, math is everywhere. So next time we turn on our computer or even a light switch, listen to some music, watch television or whatever, we should remember that at some point through history, it all started with Pythagorean Theorem and some abstraction onto the unit circle, and then some manipulation, understanding of these different ratios, then translation into graphical form, and through more and more processes into digital, and then again, by pairing different materials and other mathematical techniques, we get this wonderful world of technology that we have today. Okay? Thank you.